So, good afternoon, good morning, and good evening to everyone. Doesn't matter in which time zone you live. So I'm glad to see all of you here. And of course, I'm glad that Humberto, you agreed to give us a lecture on the economics of climate change. And first of all, our dear guest, I want to introduce you to our esteemed guest, Humberto Llavador. Humberto Llavador, he's an associate professor of economics at the University Pompeu Fabra in Barcelona. He's also a researcher. His research focuses on economics of climate change, political economy, and welfare. And also, the most relevant thing was that Humberto is the IEO advisory board member. So again, thanks that you agreed to give us a lecture, and I give you floor.
Okay, thank you very much. Thanks for the invitation and the possibility about talking about this topic that I think it's very relevant and should have all your interest and the interest of many economists. So first of all, let me congratulate you with because of the opportunity that you have to be in Hong Kong in this great event. So I wish I were there. So unfortunately, I have to be here online. It's a second best. But I think so. I've been in previous instances of the International Economic Olympiad. It's always a great event. It's a fantastic opportunity. I've been in touch with students who have participated in the International Economic Olympiad and have visited Barcelona, the Pompeu Fabra University or the Barcelona School of Economics afterwards. And everybody keeps a very warm and nice memory of their experience at the Olympiad. Beyond that, let me say a little bit, make a little bit of an introduction of what this guest lecture is going to be about. So it has an ambitious title, that it's the economics of climate change. Of course, I will not be able to talk about the whole topic of economics of climate change, because basically climate change affects all the areas of economics. There's influence in the microeconomics, in macroeconomics, in finance, in behavioral, or industrial organization. So it really affects, and it's affecting, and it has it's a very first-rated and prime topic right now among economists. So I have amended a little bit the title. It says a glance at. I should be even a bit more modest and say a glance at some aspects of the economics of climate change. Okay. So I will be, because this is online, and online in terms of questions is always a little bit harder to manage. So I don't have access to the chat, but Julia will be collecting the questions. Most of them probably I will defer to the end, but if there are any questions, especially clarifying questions, feel free to ask during the presentations, and I'm happy to be interrupted if there is something we want to, you need to clarify. So we are going to talk about the economics of climate change, and I like this topic, especially for this particular event, because it shows that if you are interested in economics, you have to have research-wise a very open mind. Economics of climate change goes beyond economics. It has to do with climate change. It has to do with climate science. It has to do with social societies, with behavior, with a change of paradigm. And in order to understand it or to say something relevant about it, it's important to understand that economics is not an actually isolated event in society, but really it's intertwined with all the other aspects of our lives. So let me start by saying the 5 things I'm gonna mention during this topic. So first, let's talk a little bit about what it's climate change. Everybody has heard about climate change, but let me try to tell you what I think it's relevant, at least from the point and the mentality of an economist. I'll mention 3 relevant facts that I think they set a good framework in order to set and start thinking about climate change from an economic perspective, and then use some of these facts to answer 2 questions or 3 questions that are relevant. First, it will be clear that we have to reduce emissions. That should be, so everybody should know that by now, but how can we reduce emissions? And in particular, how can we structure our way of thinking in order to put a structure in all the possibilities of reducing emissions. Second, well, we want to know what have we done, and if we have made any progress, how have we done this type of progress? Because at the end, what we want to know is, can we do something? Are we still on time? Are we in the right path? And economics has a lot to say on this type of topics. Okay, so let's start talking about CO2 concentrations and temperature. That it's really the key. So it's the definition of what it's behind climate change. So when we talk about climate change, a lot of people have in mind the idea of the polar bear, or so that it's in this small piece of ice, and this type of pictures. I like something a little bit more scientific. So here what you have is what it's called the Keeling curve. It's called Keeling curve because it was Charles David Keeling, who was a professor at UC San Diego, who since 1958 started going every day to the top of the Mauna Loa Observatory to collect what was the concentration, that is the amount of CO2 that it's in the atmosphere. And this concentration is measured in ppb, that's parts per million. You can think of it's kind of the density of CO2 that there is in the atmosphere. He had a very different objective than its climate change, but what he observed, and that's what we see here, is that during this period, all these observations that are daily observations, there has been a trend, an upward trend since 58 until today. They're still collecting daily observations of this concentration of CO2. The other thing we observe is this kind of spikes going up and down. This up and down, it's very natural. It's the idea, it's the breathing of the earth. It's basically the season. It's winter and summer in the northern hemisphere. So in winter, all the leaves fall, and then there are more release of CO2. Spring, then all the vegetation starts capturing CO2, and therefore there is a decline in concentration. So the spike going up and down is very natural. The trend, well, it's something that need to be that in a way it need to be explained. So in order to show you as an anecdote how precise these scientists are in collecting this type of data, there is even this small period in blue that you can observe here, and this is the period where actually the Mauna Loa erupted and they couldn't go up and collect the information. So they went to the Mauna Kea, that it's the volcano nearby, in order to collect the data. And there is this idea that saying, well, this data is not collected exactly from the same spot, but we can see that there is no change in the tendency, right? So we see this trend, this upward trend, and that it's daily collection of data can be complemented. So what we would like is to know if this is something new, it's something that has happened in the past. So what scientists do is they complement this information with actually data that is obtained from the ice cores. So one way to collect information about what was the concentration of CO2 in the atmosphere in the past, and also what was the temperature, is to dig these holes in the North Pole and trying to get these ice cores. So this is what you see here is a section of the ice cores, and in these ice cores what we observe in a more precise way of measuring, but we observe different colors, different grades of darker and lighter periods that actually reflect what was the way the ice was formed, where darker periods reflect a colder temperature, lighter, it's less density in the ice, and therefore a warmer in relative, so not so cold temperature. So these arrows represent different years. Actually, they represent the summers. So you see the summer is always lighter. There are years that they were colder. There are years that they were warmer. And as we go down, because this is ice that is being accumulated one on top of the other over the years, as we go deeper and deeper in these holes, actually it's like traveling back in time in terms of temperature. Not only temperature, but if you see these small dots here, these are actually bubbles of air. So these bubbles of air can contain air from the period, and we can date the period where they happen. They contain air, and we can extract, or scientists can extract fairly precisely what is the concentration of CO2 that there was in the air at that time. So using more sophisticated technology than what I just said, but with this source of information, they can go back in time. And here, what we see is, from an economic perspective, it makes sense to start talking about the Industrial Revolution, 1750. And what we see is that pre-industrial, what is considered the pre-industrial level of concentration of CO2 was around 280. There are some variations. Of course, we don't have daily observations, but we have a fairly good recollection of data. So 280 ppm parts per million is what is considered the reference level to see what's been the implication of the Industrial Revolution and the use of fossil fuels. So right now, and right now it means July 22nd, just a few days back, and actually if today you go to the Killing Curve webpage, you can see what's the level today. Today we have 425, around 425 parts per million. So we see that there has been this increase. This increase coincides really with the Industrial Revolution and starting using fossil fuels. But we can go even farther back in time. So this is 10,000 years ago. So we see something that we knew. We are in a temperate period. So there is an increase in temperature. So in terms of concentration of CO2 in the atmosphere, and then there is this spike. This is really the Industrial Revolution, 280, and we see perspective in time how there is this massive increase in the concentration of CO2 in the atmosphere. We can go even farther back in time, and so far scientists have reached 800,000 years ago. So when you see this, it's good to have some reference. So 800,000, it's a very large amount, and it's good to have the reference. So yes, for you to give you an idea of what period of the Earth we are talking. So this is the appearance of Homo sapiens around 300,000 years ago. This is the last ice age that coincides with a very low level of concentration of CO2, because as I will show you, higher concentration is very related with higher temperature. And this is what is the pre-industrial level. It shows that we live, so civilization have lived in a temperate period of the Earth. The Earth has gone through several ice ages, but we live in a temperate period. This is the current level, and that's actually, it's a very good image of what climate change means. It means a rapid, very fast increase in the concentration of CO2 in the atmosphere. Observe that this concentration of CO2, the difference between the pre-industrial level and today's level, is actually bigger than the difference between the concentration during the last ice age and the pre-industrial level. Okay, so why this concentration of CO2 in the atmosphere is so relevant? Well, it's very relevant because here I just show you the correlation, because there is a very good correlation, and we also know the mechanisms between the concentration of CO2 and the average temperature of the Earth. Okay, so here in dark blue, what you see is exactly the same graph we saw before, except there is no, we should have here what happened after the Industrial Revolution, this straight line. So in light blue, what you see is been the temperature that we have obtained, the average temperature on the Earth as we have obtained from the ice cores. Okay, so you see that higher concentrations are very closely linked to higher temperatures, but there is also a lag, and this is the thing. So the thing is, now we have seen a huge increase in the concentration of CO2. So we are in 400 something. We are further up here. This, for what we know, will imply an increase in the temperature. Okay, and there is a lag between one and the other. So what is crucial here is not so much that the level of concentration and the temperature will be higher, is actually that the process it's happening very fast. So if we compare with past periods, so this increase in the concentration of CO2, it has happened in very short period, and that's very clear if you look at this type of graphs where we see just a straight line. So again, so the level is not that problematic, because if we go even further back, so far we have seen this small period of the Earth, and this is the part we are talking about climate change. So in the past, and here we cannot use the ice cores, but there are other type of information or other sources to get this information. So here we are going back 65 million years. So this is kind of the disappearance of the dinosaurs. Okay, so what we see is that the Earth has had situations where the concentration of CO2 was much higher. And there was life, there was vegetation. Actually, if you see, and this is one recreation of what's the topography and the vegetation of the Earth in the period of the Eocene. So Eocene is between 65 and 35 million years ago. So if you check the difference, so there were a lot of vegetation. Actually, the two, this is the distribution right now. The two things that can be highlighted from this picture. The first one is that there is the disappearance of the ice from the South Pole, okay? And that produced an increase in the level of the sea, that you can see that there is big parts that right now, so we have land that they will be covered by the waters, okay? The second thing we observe is that you see all the northern hemisphere close to the North Pole, that it's all with huge vegetation. So these are forests, different types of even tropical. So not tropical forest here, but here we have temperate forest going all the way to the north. Okay, so could we live in this type of environment? Of course we could. Life would have no problem living here. The problem is that if the transition is very fast, we will not have the time to adjust, and the cost of adjustment, it will be very huge. It will be huge. So again, so the message from here is the idea that the problem with climate change is not so much that temperature will increase, is that actually it will increase and will affect the situation, the world. It will affect the world where we have to live in very fast. And it will not give us, and when I say us, we can't think about humans, but we could think about animals or even vegetation. So won't give us the opportunity, or it could give us the time in order to adjust without a huge cost. Okay. So with that, should be clear that that climate, that we have a situation that it's important and it's urgent. It's urgent because it's happening very fast. Let me just then talk about three interesting facts that are important for what I want to mention later. So the first one, so the three facts are actually, the first one is that it's obvious right now that humans are the cause, of climate change. And actually the models with whom we work are models that are quite good at predicting what's going to happen. The second one is that emissions, that it's the origin of this climate change, emissions of different greenhouse gases are closely linked to the economy. And the third one is that actually there is an almost near relationship between what is the cumulative, all the emissions that humans, all the amount of all the tons of CO2 that humans have emitted since the Industrial Revolution, and what is the short-term temperature increases. That is the increase in temperature, let's say, from here to the end of the century. So let me go to each one. So this is a graph from the last report. So this is the assessment report 6 of the IPCC. So the IPCC is the collection of scientists who want to put together what is the state of the art in terms of knowledge that we know, and there is a part that it's the physical environment that it's the one focusing here, but there is a part that it has to do with also with the economy and other aspects. But here, so this is what they have reached in the last IPCC, which is from a year ago, that it's unequivocal that humans' influence has warmed the atmosphere, ocean, and land. And actually, in order to, there are many different sources of supporting this statement, but this one, it's very clear. Here, what we have is, so we have in dark, so the black line, it's the observed changes in temperature with respect to the pre-industrial level. The shaded brown area is actually the predictions of the models that we have. So the first observation is that actually models are quite good at predicting, at reproducing what we have observed. And some of these models, they predicted what happened during this period, and then we've seen that temperature has moved in this within these boundaries. So it's not a bad prediction. Second is that once, and this is the important part, once we have a model that is able to simulate how the temperature will evolve, we can exclude in this model the human component. That is, let's try to have all the natural components, that is solar impact, organic impact, another type of sources in the change in temperature, and let's exclude from the model the human component. That is emissions of fossil fuels, mainly coal, oil, and gas. Then what we observe, and this is the green area, this is the green line, what we observe is that this increase in temperature would not have happened. So we are pretty much at the same level as we were during prior to the Industrial Revolution. So it's clear that it's humans, and in particular the burning of fossil fuels, that has produced the increase in temperatures that we observe right now, that it's around 1.1, 1.2 degrees with respect to temperature in the pre-industrial time. So first, models are good, And second, humans are the cause of this climate change, because when we exclude human intervention, we don't observe what we had. The second part.
Humberto,
Yes.
we have a question from the chat,
Sure.
and it is about the previous graphic. Yes, so the question is, why graph is at low during 1880 and 1930? So why is it low?
I mean, that's a question for climate scientists. Okay, so from the perspective of economists, what we want to know is that we want to rely and to make sure that the models that we are using. So I don't know exactly why we have these decreases here, because so for me, what is relevant is that the information as economists that we are using from climate scientists is an information. It's a good question, and but I don't know the reason of this particular events here. So there are a lot of variations, like the increase that we have here. So it might be, I don't know. So they could be related to something in particular. Maybe someone knows about this. So the second thing is that when we put the change in temperature, and we compare the cumulative emissions, that is all the tons or gigatons of CO2 that we have emitted since the Industrial Revolution, then what we observe is that there is a relation that is almost linear. That is, we could predict with some being quite not the prediction would not be too bad if we consider if we want to predict the change in temperature, if we just take into account everything we have emitted. And actually this relationship, it's almost linear, and there is this constant that it's called the transient climate response to cumulative carbon emissions that says every 1,000 gigatons of CO2 that we have emitted, this will imply a certain increase in temperature. Okay, and this is fairly constant over time. There is so which implies that for short-term effects, and when we talk about short-term effects, we are thinking from here to the end of the century. So we may focus on the total amount of CO2 we have emitted. So it's not so important the path. So have we emitted a lot at this period? But really focusing on the total emissions, it's a very good first approximation. So this estimation is around. So there is a range, but the best estimate is around 0.45. What means is that for every 1,000 gigatons of CO2 that we have emitted, the average temperature on the Earth has increased in 0.45 degrees. And this actually is consistent with the idea that given the temperature we have emitted, now given the CO2 we have emitted, now the temperature has increased around 1.1 degrees. So this linear relationship is very relevant because it tells us two things. So the first one is that all emissions matter, because since what is relevant is how many tons of CO2 we have emitted in total, every ton we emit contributes to this increase in CO2. The second relevant fact is that if we want to stop increasing temperature, no matter what's the level we want to set, if we have a target, there is a moment where we have to reduce emissions to zero. Could be 1.5 degrees, it could be 2 degrees. We could even think about 5 degrees. There is a moment where we have to stop emitting for this increase in temperature. And actually that allows us, and here what you have are possible scenarios of once we set a target of 1.5 degrees, so we have different smooth paths of reducing emissions and still reaching this target. So of course, so this is the black line is the actual emissions. Of course, the sooner we start reducing emissions, the smoother can be the path in order to not exceed the carbon budget, the total amount of CO2 that we have in order to not surpass the target of 1.5 degrees. Here, what you have is, so this would be, this is the path. If we start reducing, this graph is from 2019, if we started reducing emissions in 2020, we should follow, this is, it doesn't need to be this, it needs, but we should follow this. This is a possible smooth path of emissions. That when you see this path, actually it should make clear why, when we hear about climate change and the possible targets and the policies, there are two dates that come to mind. One is 2030. Why? Because if we follow this path, in 2030, we have emitted all our, we have used of our carbon budget for 1.5 degrees, and then it's not possible to find a path that reaches this 1.5 degrees. The second is 2050. Why? Because in 2050 is where, if we want to follow this smooth path, around 2050 is when we have to reach the zero. We have to reach zero emissions, so we have to move to a no emissions economic framework. Okay, so these are just reference points, but it tells you this idea that thinking about the carbon budget, thinking that we have a certain amount of CO2 to use, and once we use it, we have to move to a different target. So it really it's behind. It's a good approximation to understand what are the type of policies we have to do. Of course, if we have, so I think I have to change 1 second. So if we have a less restrictive target, if rather than 1.5 degrees, what we want is to reach 2 degrees, then we have a larger budget and the path can be smoother even in 2020. We don't need to decline emissions that fast, but of course we have to live with the consequences of a 2 degrees increase in temperature rather than 1.5 degrees. Okay. Now, third point is that these emissions are closely linked to the economic activity. So let me just show you this graph. These are the annual emissions of CO2. Okay, so this is global emissions. This is global emissions in the world since pre-industrial level, and these are human emissions of from fossil fuels, from coal, oil, and gas. And what we see is with the Industrial Revolution, emissions start increasing. What is interesting is that we can identify every single dip that we see in this graph. So the first one, so what's that dip? That actually, if you can guess, that's actually World War I. What about the second one? This one. So that's where do we have a recession that we reduce production? That's actually the crisis of the 29. Third one, it's World War II. Then we go all the way up here, where what we have is the crisis of the 73. And we see the decline in emissions, crisis of 73, very closely related to the use of fossil fuels. So there is this agreement among oil producers. They reduce production. There is this crisis. Production is they reduce the production of oil. There is a crisis, reduction in production, reduction of the economy, crisis of 73, crisis of 79, not as big, but still noticeable. This one is actually the only crisis that it's not a global crisis, but a local crisis that you can see because of the relevance and the impact that it had. the only crisis that is local that you can see at the global level, and that's the fall of the USSR. That actually, in economic terms, had an impact sufficiently large in order to be seen at the global level. We have in comparison, in quotes, the small crisis of 2008, and as everybody guessed, so what's that? That's actually COVID-19. So this fall, so this stop in production, it really reduces the emissions. So this tells us two things. So it really, there is this link between the economy and emissions. The second message you can get from here is that if now we want to go to reducing emissions to zero, well, if we want to reduce emissions to zero only by reducing production, well, the impact is going to be huge. Because think about the impact of COVID-19, think about the crisis of 29, and how relevant they were in reducing total emissions. It's really small. And actually we recover, we didn't learn the lesson, and we recovered very quickly to the previous, basically to following the path. So we see, the other thing we see is that emissions has not declined, but it's true that emissions are slowing down the increase. Okay. So just in terms of emissions, just to be, let me just add a note to say why we focus so much in CO2. Because if you look at emissions, so first, energy is really what is important in terms of where all the emissions are happening. Mostly electricity, heat, and manufacturing and transportation. Okay, this of course varies for different countries. In the case, for example, in the case of India, agriculture has much higher share of emissions. In the case of production, China has much higher share of emissions. In Europe, transportation has, and the US has a much higher share in the generation of emissions. But in terms of what are the greenhouse gases that affect warming, by far the most relevant is CO2, and we should talk about methane as well. There is some details here that I'm not going to enter because it also depends on how, so whether it's a very intense short-term impact or it's a very long-term impact, but I would say CO2 and methane are the most relevant. But something to keep in mind is that it's easy to remember, 75% of all emissions come from energy, around 75% of all emissions comes from CO2. And this is why the focus on CO2 and energy. Okay, so we know we have to reduce emissions. Now, if I ask, so it's this is one of the disadvantages of having the presentation online. But if I were there, I could ask, I can ask you to think, well, how? Think about measures to reduce emissions. If we had that opportunity and we started adding all the measures to reduce emissions, we'll end up with a blackboard full of possible alternatives. And what we would like is to see if we can structure, and every one of us can think of 20, 25 different ways of reducing emissions. But what we would like is to structure all these measures in a way that help us in order to analyze this reduction of emissions. And for that, one thing that is very useful is what is called the Kaya identity, and this case should be capital letter because this is a person who made this proposal. That starts from very simple and kind of tautological equality that says the amount of CO2 emitted is equal to the amount of CO2 emitted. I think we all can agree on that. But if I do that, what I can do is to say, well, actually the amount of CO2 emitted, it depends on how much CO2 is in the energy I use times the energy I use. So this is what is called carbon intensity, which says the energy I'm using has a content of CO2, and the more intense the use of carbon in our energy, the higher the emission of CO2. But actually, the energy we use depends on how much we produce. That is, what we are producing, and observe that I'm multiplying and dividing by the short term all the time, so we maintain this identity. So the energy I'm producing is equal to the energy intensity of our production times the quantity we produce, and the quantity we produce can be divided between how much we produce per capita and how many people we are. If we all agree with this, which is an identity, we have, if we cancel everything, we end up CO2 equal to CO2. So what it says is that if we want to reduce emissions of CO2, there are only 4 ways to do this. The first one is we could reduce population. Okay, so this is a policy that, for obvious ethical reasons, is not discussed as an option, but there is a tendency in the trend of the population in the Earth, where we are reducing the growth of population, and the forecast is that population probably will stabilize around 2060, 2070. Still, many more than we are right now. But if we don't reduce population, another possibility is to reduce consumption per capita. We could reduce consumption, or we could be more efficient in the use of our technology. Observe that this is the energy used in our production. Here it could be more efficient, or we could change our habits. We could end up consuming things that are less intensive in energy. Or we could reduce the CO2 content of our energy, and this is actually what it's renewable energy. This doesn't mean that they are exclusive. We could have a combination of all of them. And that's actually where all the policies are coming. Are policies that they say, we are trying to go through this transition towards renewable energy in order to reduce the content of CO2 in the energy. We are trying to be more efficient in technology. We are trying to reduce consumption. And there is this tendency about population. So the only thing that is not captured here is actually geoengineering, that so far is a little bit more wishful thinking than really an actual policy. So this is, I think, a very good way to start thinking and structuring your thought when you think about the different policies for reducing emissions. Okay, so now that we have that,
we also again have a question about this topic. So the question is, how agriculture emits CO2 and at 11.2%?
So agriculture emits CO2 in many different ways. One is by clearing forests, right? If you cut the trees and you transform that into agriculture, then these trees, they were capturing CO2. Sometimes you cut them, sometimes you burn them. This is, for example, what is happening in the Amazons. So that's one way to reduce. The other is when we talk about agriculture, sometimes agriculture is connected also with the use of cattle. So cattle and meat production generates a lot of emission, mostly methane, but not only, but also CO2. Agriculture, other type of emissions is agriculture that uses, for example, rice is cultivating rice is a big source of methane as well, because there is this still water that generates this methane. But usually the agriculture, besides that, it's also the use of all the machinery that is associated to agriculture. Okay. So once we have, so I hope I answer the question. So once we have this for structure, these 4 components of emissions, then we could try to think how we have done. And here, what you see is these are emissions. So this is all the emissions And what we see is emissions have not declined, but they are kind of stabilizing, while at the same time, population and GDP per capita has been increasing. So what we observe is that there is a partial decoupling, and this is during the last 10, 30 years, partial decoupling of GDP and emissions. We have been able to be more people, to consume more per capita, while emissions have not increased at the same rate. They have increased, but they have not increased at the rate as GDP and population could predict. So how have we done that? So we have done that, and this is where the Kairos identity helps us, mostly because we have been way more efficient in using energy. Okay, so we have been able to use less energy to produce the same amount of product, or to produce more product. And that really, so if you compare to 1997, here we are talking about very recent period, compared to 1997, so the amount of carbon intensity or energy intensity of GDP has fallen around 25%. Okay, we have not done that well in the terms of the use of green energy. So green energy, that is what's the carbon intensity, what is the CO2 in the energy we use, it has barely changed, except perhaps in the last years. So this increases a little bit more, and this is mostly, as we'll see in the next graph, especially because of the decline in the OECD countries. Okay, so there are two ways to see this. So first, so the main message is what we observe is that world mitigation gains have been driven mostly by energy efficiency and not really about green energy. So here you can see the half empty or the half full glass. So the half empty glass is to be a little bit pessimistic and say, oh, look, we haven't done what we should have done. The half full glass, it says, look, we have managed to obtain something and we still have a bullet, that it's the green energy that we haven't used yet. So that's something that still have there, and we have that policy and that opportunity in order to reduce emissions. And then you see and you start understanding why all the emphasis on the energy transition, that it's gaining a lot of attention in the media, and also in the policies of the different countries and the COPs. Okay. Now, as I told you, so this image changes a little bit if you look at the OECD countries. This is the same graph we saw before. If we look at the OECD countries in the last 10, 15 years, even a little bit further, what they have seen is a decline both of emissions, and that's the CO2 emissions. So here we really see a decline in CO2 emissions, and this decline in CO2 emissions is mostly because of energy intensity, but there is also a decline because of the use of renewable energies. And this is 2017. So this is something, it's a tendency that we are observing in the last years. So these changes have made, so let me try to finish with a more, so it looks like a very grim prospect. So let's try to be a little bit optimistic, and let's see if we have made any progress. And let's look at the last 10, 15 years. Okay, so this is a graph that shows, so these are greenhouse actual emissions, and this is the path that when we were in 2010, what was the forecast of where emissions would go and what was the increase in temperature. So of course, as any forecast, as we move further in time, the range, the uncertainty increases, but what we know is that in 2010, when we were in 2010, when I was researching this type of topics in 2010, what we were talking is that if we do nothing, we are going to end up with 4 or 5 degrees increases in temperature by the end of the century. And this is 2010. We are talking 15 years ago. Since then, with the policies we have adopted in the last, mostly the last 10 years, and very closely related with the Paris Agreement, with the current policies, without doing anything more than what the current policies, the increase in temperature, it's around 3 degrees. This is the predicted, if we do nothing else. Of course, 3 degrees is still a huge increase in temperature, but observe that in 10 years, we have managed to decrease temperature, the forecast of temperature, in 2 degrees, approximately, right? If we believe that countries will fulfill their promises in the Paris Agreement, that is, their pledges and targets, because remember, the Paris Agreement is an agreement in which each country decides or make public what are their intentions to fulfill of their policies. One is current policies, the other one is that intentions. If they fulfill their intentions, then the increase in temperature, it will be 2.4. This is still far from what we would like, that it's 2 or even better, 1.5 degrees. Okay, but the idea, and this is something that I think usually it's forgotten, is that in 10 years, we have managed to make a difference. We still have time to make a difference. That doesn't mean that it's going to come by itself. We have to do it, but there is still the possibility to go to these paths where we can go to 2 degrees and 1.5 degrees that are from a technological, economic, technological and economic perspective, they are feasible. It's something that we can obtain. Okay, so again, so these are the 4 things. So again, you can see the picture as the half-empty glass or the half-full glass. So the half-empty glass, it's the pessimistic view. You focus on this part and you say, oh, look, current policies, we are still very far from where we have to go. Or you can see it as half full and saying, look, in 10 years, we have managed to decrease 2 degrees. So we still have time if we want to go even further if we take the right policies. So the question is, well, which one are you? And no matter which one you are, what it should drive you is to say, in any case, whether I see it half full or half empty, we can. So it should move you in order to take the measures that are relevant in order to reduce these emissions. Of course, that doesn't mean that what is ahead, it's going to be very easy. And there are many thorny issues. And these thorny issues are actually what is relevant from economic research. And let me just highlight the points in order to show you how interesting can be to do research in economics and where the research in economics is focusing right now. Mostly, among other things, first, on trying to estimate climate damages and estimation of abatement cost. We know we have to reduce emissions to 0, but how fast and what's the best way depends on how, what parts will be affected, how much will be affected by the change on the climate, and how much, how costly it is to go into to reduce these emissions. But not only is it important to have this aggregate picture, but there is a lot of research going on into how is the distribution of these climate damages, the distribution of this cost of abatement, cost of mitigation, of reducing emissions, the distribution both intragenerational, that is among the countries right now, as well, and this is something very specific and relevant in the case of climate change, intergenerational, and something that should be a big concern for you in terms of current generations, future generations, because many of the people who are right now making this type of decisions probably will not suffer or will not enjoy the consequences, good or bad, of the policies we are making there. In an aspect a little bit more technical, but not less crucial, uncertainty is a key issue here, because there are aspects that. So we know a lot, but there is still aspect that should push us to be cautious and to use the precautionary principle in many of the aspects and the policies that we implement. Okay, so thanks a lot, and I hope you learn anything here, and good luck in your tasks that you already have ahead. Enjoy your time there in the Olympiad, meeting people, learning a lot, and I think it's an experience. And again, so I have a very healthy, but still a little bit envious of you being there and me still here in my office working. So thanks a lot.
Yeah, thank you very much. Thank you that you covered different topics, and it was very interesting. And we have a couple of minutes, and we have like one general question in our chat. So what should be done to preserve the climate? So maybe preserve the climate. So maybe what are the advices, what we can do ourselves to improve the situation?
So this is the question that always comes after this type of talk, that it's what can I do as an individual citizen to make a difference? My answer is always the same. What you can do is support governments who support this type of measures. So what we have to do, and we all have to do, so the biggest impact you can have is support organizations, governments, decision makers at all levels who put climate change as the priority level, so at the priority level. So that's the biggest impact. Besides that, and connecting with that, there are minor things that are relevant. So in your daily life, it's important to take in consideration all the 4 aspects in which you can reduce climate change. I'm not going to talk about population, but it's true that we can change our habits. It's true that we can try to focus on products that have lower content, if we think of it from the aspect of consumption. And this could be goods, services, energy, and so on, that has lower content of energy. But again, so we have to be conscious that we can make an impact, a small impact individually, but this small impact can aggregate, but we cannot solve everything by ourselves. So if we really want to have an impact, let's try to force governments to take climate change seriously and focus on it and take the measures that are necessary to be taken.
Yeah, thank you very much. And there is another question. How you see machine learning in economics for better predictions?
Sorry?
How you see machine learning in economics for better predictions?
So machine learning has been used. So in terms of climate, there are some studies that are starting to use machine learning. Is not the dominant research time right now because it's a field that it's starting. So I think it's an area. So whenever there is nothing else on research, that's in quotes from a perspective of a researcher, great news, because it means there is still a very open area where a lot can be done. So I think it will. So machine learning will help a lot in specifics of different policies. If we think about implementation of policies related to energy transition, for example, solar panels, distribution of the area of solar and aeolic energy. Okay, so winds and are relevant in order to determine what's probably the best setting in order to be the most efficient in the use of this type of new technology, as well as for the behavior of people. that it's crucial. Behavior, remember, it's one of the crucial aspects of economics.
Yeah, thank you. And maybe we have the last question. Will the government listen or even give it consideration?
Could the government, sorry?
Listen or even give it consideration. So maybe, yeah.
So the issue about, so if you realize when I said, so economic, where I said that from an economic and technological perspective, we know that it's feasible to reach this 1.5 degrees. The big challenge is whether we will manage to do it from a political perspective. But there we have to think in two aspects. It's true. So there are governments that they have done a lot, or they have contributed and they have participated and they have pushed a lot the climate change agenda. We have to think, and that's very linked to the first questions, we have to think that we also, as a society, have the possibility to influence and have an impact on governments. Whether governments will agree, will take the measures or not, I think that's something that nobody can say right now. But at least my perspective is, I hope that I can say at least I tried.
Yeah. So maybe we don't have any questions. So thanks again for coming. Thank you for your supportive words to our contestants. Yeah, thank you very much.
Okay, thanks a lot. Thanks for the opportunity. And as I said, enjoy the rest of your stay there.
Yeah, and our contestants also, thank you for your lecture.
Okay.
Yeah.